Within linear algebra, elementary matrix operations are a very important tool for solving systems of equations. Here we got a random matrix. I picked it in a random generator. And we're going to show with some examples what elementary operations are and what the elementary matrix is and how you construct them. So what you can do with this system without changing the solution for the equation system. So each equation system that this matrix represents has a set of solutions. And elementary matrix operations doesn't change the set. That's why this can be used to solve systems of equations. So without changing the set of the equation system embedded in this matrix, you are allowed to do 3 types of operations. First, and the most simple one, is to change, or maybe swap. We can call it swap. Swap the rows, meaning that we would change these in like this. So this row become the middle row. I'm going to show examples later. Or you're allowed to multiply a row with scalar c that's non-zero. Or you're allowed to add rows to each other. So these are the 3 elementary matrix operations that exist. And if we perform these on this matrix here, we're going to make a little copy of this and move it below to make some examples. Copy to clipboard. Thank you very much. And paste it here. So if we would like to do some operations here, if we're going to implement the first rule here in any manner, we could do a swap and exchange these two. According to rule number 1 of swapping of rows, we do get 7, 2, 2, 2, 3, 0, 8, 6, 6. So here we performed a row swap. And when we done that, we could, for example, make multiply a row with a scalar. So we multiply the mid row here with 2, getting from the second rule, we do get all the other rows stay the same. So 2, 2, these are just copy and paste rows. This row here comes 4, 6, 0. And then we could implement the third rule and add row 2 to the fourth row. I'm going to say plus 2. With the third rule. And then we would get this first row stay the same. The middle row stay the same. But this one changes. And then we're going to add 2 of this. So how do we add 2? The rule only says add a row to each other. But adding a row plus 2 is equal to first multiplying this row by 2, then adding it, and then dividing this one again. So this doesn't change. That's why it's the same on this side. But we can add a multiple of this one to this one. It's a combination of rule 2 and 3. So we get 2 times 4 is 8, plus 8, that's 16. 2 times 6 is 12, plus 6, that's 18. 2 times 0 is 0, plus 6, that's 6. So now we perform some row operations, or some that's also called elementary matrix operations on this matrix, to go from here to here. Why you do this depends on the occasion. This was just made for a little example, but these operations are used in what's called the Gauss-Jordan elimination method of matrix. And that's a very useful method for solving systems of equations without having to do substitutions and other methods you maybe have learned before. But instead, you can just do something that's called row reduction, and this matrix will show the answers of the systems of equations. This video is not about that, so you'll have to go check for another one. But now we're going to look into what's called elementary matrices. So you might heard of those, and they say that you can represent the elementary matrix operations within an elementary matrix, and then that one would be equal to multiply the first matrix with the elementary matrix for the operations that happens to end up in the last stage. So what does this mean? First of all, if we take a little friend here again, the first matrix we start with, paste. We move up there. There's something called identity matrix. And the identity matrix, oh no, what did I do? There. The identity matrix is this familiar face with ones along the diagonal and zeros in the rest of the places. And performing matrix multiplication, we do get the same thing that we had here. So this is exactly like matrix 1, like the 1 for the matrix multiplication. It's the identity. So nothing changes in this multiplication because this is the identity matrix. But we had some rules that were elementary row operations. And to get an elementary matrix operations, we perform the row operations, or the matrix operations, on the identity matrix. So if we get to this one here, I'm going to show you this by example. So take the identity matrix, and then we do the same thing we did up here. We did the row swap on the first and the second row. We do it on the identity matrix. Whoop. Using the first row. Then we get this row on the top. 0, 1, 0. Then we get this row. 1, 0, 0. And then we get the unchanged row down here. All right. So this is the elementary row operation matrix for this row operation. Swap rows on the first row. And what you get is that if you do this multiplication we did up here, go down here, and we add our matrix here once more, the one we use in our examples, and we multiply this with this new matrix instead of the matrix, the identity matrix. So we're going to add this matrix here instead. You can try this out yourself by performing some matrix multiplication on your paper. That's a very good practice to do. And you will notice that this matrix generates this. So this generated the same result as the row operation did up here. Why is this important? It is important because in this manner, you can do in a more automatic way, store the different ways you performed your elementary matrix operations like this. So I said here, swap row. And then I said, multiply mid row by 2. And then I said, add 2 of the second row to the last row. So this is quite a long thing to do, but you could summarize this within an elementary matrix like this. So if we would continue performing our row operations on this matrix, we would in the end up with a matrix that just by a simple multiplication like this would take us all the way from this stage with one simple multiplication. And you realize that when doing this in a grand scale of something like 1,000 matrices, and when the computer calculates on them, that's a much more efficient way than doing this by hand. So it's a very important connection with this. Then the rule is also that elementary matrix operations doesn't change the as I mentioned in the beginning, it doesn't change the solution set for the original equation system. So this is very useful for automating algorithms in computers to solve systems of equations. And they usually use what I mentioned before was called the Gauss-Jordan elimination method. And there's probably some interesting Wikipedia articles on that topic. And that was everything for this video. I will go deeper into linear algebra in the near future. If you have any questions, please give me some comments. Also comments about sound quality and those things. I want those to improve as much as possible. And I'll hear you in the future. Good luck with your maths.